Hello and welcome back. In the previous two videos, we discussed the interference that can occur when light passes through a single slit or multiple slits. And in this video, I want to talk about a different type of interference that can occur when light reflects off the two surfaces of a thin film. So the basic idea is that if light shines on a film, some of this light can reflect off of the top surface of the film, while some of the light will travel through that and reflect off of the bottom surface of the film. And then these two reflected waves can interfere with each other and produce an interference pattern. Now, it turns out that there are two things about this type of interference that make it a little bit more difficult than the slit interference that we discussed in the previous two videos. And the first thing that I'd like to talk about are the changes that can occur to the wavelength of light when it moves from one material into another. And it turns out that this is very closely related to the speed of light as it moves through a material. And so it turns out that most waves, when they move from one material into another, the speed of this wave will change. For example, the speed of sound is faster in water than it is in air. And for light, we describe the speed of light through a material in terms of something called the index of refraction. And we define the index of refraction with this formula right here. So we say the speed that light moves through a particular material is equal to the speed of light traveling in vacuum divided by the index of refraction of that material. Now, because light always slows down when it's moving through a material, this index of refraction is always going to be a number that's greater than 1. See, we're always going to be dividing the speed of light in vacuum by a number greater than 1 to give us something that's smaller than that. So typical values of the index of refraction I have listed here. So the index of refraction in air is approximately equal to 1. So that means that air really doesn't slow down light very much. The index of refraction of water is almost exactly equal to 4/3. It's actually pretty ridiculous how close it is. I think like room temperature, I think the index of refraction of water is something like 1.333. And the index of refraction of glass is usually pretty close to 3/2. And of course, that depends on what the glass is made out of, whether it's a crystalline quartz or an amorphous type of silica. But most forms of glass have an index of refraction that's very close to 1.5. Recall that the speed that a wave is traveling at is related to the frequency and wavelength according to this formula right here. And so what this means is that if the speed of a wave changes when the wave moves from one material into another, then either the frequency or the wavelength also has to change. And an important thing to understand is that the frequency of a wave doesn't depend on the speed that the wave is traveling. It doesn't depend on the material that the wave is traveling through. And to understand why that is, imagine generating a wave on a string. So imagine you have a real long string and you're moving one end of the string up and down to generate a wave on it. Well, the frequency of this wave, that's how quickly it moves up and down, is determined by how quickly you move the end of the rope up and down. So in other words, you choose the frequency when you generate a wave on a string. Now, the wavelength of this wave is going to be determined by the speed of the wave, and you have no control over that. So if the wave has a very high speed, then it'll have a very large wavelength. If the wave is moving very slowly, it'll have a very small wavelength. But the important thing to understand is that the frequency of this wave was determined by how quickly you move the end of the rope up and down. So you had control over the frequency of the wave. Now, we haven't talked a whole lot about how light is generated, but it turns out that light is basically made by charged particles moving up and down. And so the frequency of light is determined by how quickly these charged particles move up and down. And so this is not going to be affected by the speed of light. Only the wavelength is determined by the speed of light. So what we can do is, because the speed that light travels is related to the index of refraction, we can use this formula right here to relate the wavelength of light to the index of refraction. So we have the formula that the speed of light traveling through a material is equal to the speed of light in vacuum divided by the index of refraction. Now, if I plug this formula in here, the speed of light traveling through a material is equal to the frequency of the light times the wavelength of the light in the material. And I'm going to put a little dash here to represent this as the wavelength inside a material. And this is going to be equal to the frequency of that light divided by the times the wavelength inside a vacuum divided by the index of refraction. And now I can cancel out these frequencies because they're going to be the same, and I see that the wavelength inside a material is equal to the wavelength in vacuum divided by the index of refraction. So the wavelength of light will always decrease when it moves from air into another material like glass or water. Now, because the phase of a wave is described in terms of the wave's wavelength, when you change the wavelength of a wave, you affect the wave's phase. And so this can actually cause interference patterns between two waves. So for example, down here, I have a wave that's traveling through a material that affects the wavelength of the wave. And above that, I have another wave that does not pass through material. And because of the effect that this material has on this wave's wavelength, these two waves will interfere with each other. So for example, here we have these two waves, and these two waves are starting out in phase. So we can see they're starting out at minimums here, they go up to a maximum at the same points, they're initially in phase. However, when this wave on the bottom of the screen passes through this material, its wavelength decreases. And as a result, this wave on the bottom of the screen will undergo 1/2 of an oscillation more than the wave on the top part of the screen as it moves through this material. And as a result, when this wave on the bottom of the screen leaves this material, it is now going to be out of phase with the wave that was on the top. So we can actually have phase differences arise between two waves when one wave moves through a material that changes its wavelength and the other material does not move through that material. So let's take a look at an example. This example says light with a wavelength of 586 nanometers passes through a double-slit apparatus, and the resulting interference pattern appears on a viewing screen. When a thin film of plastic with an index of refraction of 1.6 is placed over one of the slits, the interference pattern is inverted. And the question asks us to determine what the thinnest film that was placed over that slit could have been. So the basic idea is that we have this double slit apparatus, and we're going to place a thin film over top of one of these two slits. So we have light that's passing through this slit, and we have light that's passing through this slit. And this film is going to cause a phase difference between these two beams. Now, if we think about this, if I have a place where we used to have constructive interference, and then I put this film in, and now we have destructive interference, what that means is that this film is going to create a phase difference between these two waves that is exactly equal to 1/2 of a wavelength. So what we have here in this example is exactly the same thing that we had in this illustration on the slide here. So we have these two waves, and because of this film changing the wavelength of this wave that passes through the film will undergo 1/2 of a wavelength more than the wave that does not pass through the film. And so we're going to use that to calculate the thickness of this film. So let me write down the information that was given to us. So we're told that the wavelength of the light is equal to 586 nanometers, and that the index of refraction is equal to 1.6. And we need to figure out the smallest thickness that this film could be. So the idea is that the wave that travels through the film will undergo 1/2 of an oscillation more than the wave that does not travel through the film. So we need to come up with a way to calculate the number of oscillations that a wave undergoes when it travels through a certain distance. So if we think about that, the number of oscillations is going to be equal to the distance that the light travels, this length L, divided by the distance it would have to travel to undergo a single oscillation, which is its wavelength. So if I take this total length L and divide it by the wavelength, that'll tell me the number of oscillations that the wave has undergone. So the light is going to undergo more oscillations when it travels through the film. So the number of oscillations in the film minus the number of oscillations in air has to be equal to 1/2. So we're going to undergo 1/2 of an oscillation more with the light that travels through the film than the light that's traveling through the air. And we said the way we calculate this is we take the length that the light is going to travel and we divide it by the wavelength of the light. And it's very important that we are using the wavelength of the light inside the material that it's traveling through. So here the number of oscillations that the light undergoes when it travels through the film is equal to the distance that the light travels through the film divided by the wavelength of the light inside the film. And we're going to subtract that from the number of oscillations that the wave undergoes when it travels through air, and we're trying to find when that's equal to 1/2. Now remember that this wavelength is given by another formula. Let me write that over here. The wavelength of light inside a material is equal to the wavelength of light in air divided by the index of refraction inside that material. So if I plug this equation into this formula here, so I'm going to have an lambda divided by n, so this is going to give me nl divided by lambda minus L divided by lambda is equal to 1/2. And so both of these terms have an L over lambda, so I could write this as L over lambda times n minus 1. And if I solve for that length, L, I see that L is going to be equal to, so we'll have lambda divided by 2 times 1 divided by n minus 1. And if we plug this into a calculator, we can see that the thickness of the film is equal to 488 nanometers. So that is the thinnest film that'll cause a 1/2 of a wavelength phase shift between these two waves. So now that we understand how to calculate the wavelength of light inside a material, and we also understand how changes in the wavelength of a wave can affect the phase of the wave, I now want to look at what happens to the phase of a wave when the wave reflects off of the surface of a material. So in an earlier video, we discussed what happens when a wave reflects off of a free end of a string or a fixed point in a string. So recall that if a wave is traveling along a string and it reaches a fixed point in the string, then the wave that reflects off of this fixed point will be flipped upside down. Similarly, if you have a wave that's traveling along a string and it reaches the free end of the string, the wave will also be reflected off of that end, but the wave will remain right side up. And it turns out that these are actually limiting cases of a much more general phenomenon. So it turns out that whenever a wave reaches an interface between two different materials, some of the light will be reflected off of that surface and some of the light will be transmitted through. And that light that gets reflected off, sometimes that will be flipped upside down and sometimes it will remain right side up. So whenever you have light that moves from a material with a lower index of refraction into a material with a higher index of refraction, it turns out that the reflected wave will be flipped upside down. So whenever you're moving from a material where the wave moves faster into a material where the wave moves slower, that reflected light will be flipped upside down. And so here I have this kind of illustrated. So here we have the solid line representing a wave which is moving towards this interface between two materials. And when this happens, we can see the reflected wave is flipped upside down. And by looking at this, we can see that this reflected wave, this solid line is the reflected wave, we can see that this reflected wave here is exactly a 1/2 of a wavelength out of phase with this dotted line, which represented the initial wave coming in. Right? We can see that this distance right here is a 1/2 of a wavelength. In other words, I would have to move this solid curve 1/2 of a wavelength to the right so that it would overlap the initial wave. So anytime a wave moves from a material with a lower index of refraction into a material with a higher index of refraction, this causes a phase shift that is equal to a 1/2 of a wavelength. And so just to kind of illustrate this, I solved the wave equation for a wave that's traveling through a material with a low index of refraction into a material with a higher index of refraction. And so you can see here that basically we had this pulse that was moving towards the right, and when it reaches this green line here, we'll get a smaller pulse that continues to travel through, and we'll get a reflected pulse which is flipped upside down and traveling in the opposite direction. Now, conversely, if light travels from a material with a high index of refraction into a material with a lower index of refraction, so in other words, the light's moving through a material where the light moves slowly, and it reaches the interface into a material where the light moves more quickly, some of the light will reflect off of that surface, and it turns out that that light will remain right side up. So here we have this incident light that's traveling, say, through a piece of glass, and when it reaches the interface between the glass and air, the reflected wave will remain right side up. And we can see that this wave that was reflected off of the surface is in phase with the wave that continued traveling through. So whenever light travels from a material with a higher index of refraction into a material with a lower index of refraction, the reflected wave does not receive any phase shift. Okay, so you only get a half of a wavelength phase shift if you go from a material with a low index of refraction into a material with a higher index of refraction. If you reflect off a material that had a lower index of refraction, then you don't get any phase shift. And once again, just kind of illustrate this, I've again solved the wave equation for for a wave that's moving from a material with a higher index of refraction into a material with a lower index of refraction. As a couple things you can see that as the wave transmits into the material with a lower index of refraction, the disturbance gets larger. But we can also see that there is a reflected wave that remains right side up that travels back in the opposite direction. So the idea is that in thin film interference, there are two surfaces that the light can reflect off of. So you're going to have some light coming in, and some of it's going to reflect off of this front surface on a thin film, and some of that light's going to travel through and it'll reflect off of the back surface of the thin film. And so there are two places where there can be a phase shift that is caused by the reflections. There's this reflection that occurs on the front surface of the film, and this reflection that occurs on the back surface of the film. And whether or not these phase shifts are important depend on these three indices of refraction. And it turns out there's actually a really simple rule that we can use to determine whether or not these phase shifts are going to be important. So let me actually open up a blank screen because I want to kind of go into this a little bit and explain where this rule comes from. So the basic idea behind this trick is that it turns out that there are really only 4 possible cases that can occur. So the first possibility is that the index of refraction over the first interface is increasing, and the index of refraction over the second interface is also increasing. So in this case, we have the index of refraction of material 2 is greater than the index of refraction of material 1, and the index of refraction of material 3 is greater than the index of refraction of material 2. So in this case, remember that whenever a wave reflects off of a surface where the index of refraction is increasing over that surface, that reflected wave is going to experience a half of a wavelength phase shift. So the light that reflects off of this first surface, it experiences a phase shift that's equal to half of a wavelength, and the light that reflects off of the second surface, because the index of refraction is also increasing over the second surface, that light also experiences a phase shift it's equal to a half of a wavelength. Now, because these two reflected waves both experience the same phase shift, the net effect that these two phase shifts have are going to cancel out. Now, that doesn't mean that these two reflected waves are going to be in phase, because the light that reflects off of the second surface has to travel a little bit further to reach that second surface and then bounce back. But what this means is that the effects of these two phase shifts that occur at the reflections cancel out, and so we can effectively just ignore those phase shifts. Now, the other possibility is that the index of refraction increases over the first interface and then it decreases over the second interface. So we have it increasing and then decreasing. So that means that the index of refraction of material 2 is greater than it is for material 1, and the index of refraction for material 3 is less than it is for material 2. So we have a material with a high index of refraction sandwiched between two materials with a lower index of refraction. So this is, for example, what happens if you have a thin film in air. And in this case, again, in the first material, we're going through an interface where the index of refraction increases. So that means we get a phase shift that's equal to a half of a wavelength over the first interface. However, in the second interface, the index of refraction is decreasing, and that means we don't have any phase shift that occurs in the reflection on that second surface. So here the phase shift on the second surface is 0. So the overall effect of these two phase shifts is that the two waves are now going to be a half of a wavelength out of phase just due to these reflections. Now there's also, again, going to be a phase shift that occurs because the wave that travels through and hits the back side of the film is going to travel a little bit further. But just from the reflections alone, we're already going to have a phase difference between these two waves that's equal to a half of a wavelength. Now the other possibility is that the index of refraction is going to decrease over the first interface, and then it's going to be increasing over the second interface. So that means that the index of refraction of material 2 is less than it is for material 1, and the index of refraction for material 3 is going to be greater than it is for material 2. So what this means is that we have a low index of refraction material that is surrounded by two materials with a higher index of refraction. Now recall that if the index of refraction is decreasing across an interface, then the reflected wave will remain right side up, so there will be no phase shift. So over this first interface, there will be no phase shift caused by that reflection. And also remember that if the index of refraction is increasing across a interface between two materials, then the reflected wave will experience a half of a wavelength phase shift. So in the second reflection, there will be a half of a wavelength phase shift. So once again, we have one wave that's shifted by a half of a wavelength, and the other wave doesn't experience a phase shift. So here, the difference in the phases of these two waves will be equal to a half of a wavelength. Now the final possibility is that the index of refraction is decreasing across both of the interfaces. So here we have the index of refraction of material 2 is less than the index of refraction for material 1, and the index of refraction for material 3 is less than the index of refraction for material 2. Now remember that whenever the index of refraction is decreasing across an interface, there's no phase shift. And because the index of refraction is decreasing across both of these interfaces, both of the reflected waves experience no phase shift. So here, in this case, there is no phase shift for either of the two waves. So taking a step back and looking at this, if the index of refraction are always increasing, then we get a phase shift for both of the waves, and the overall effect is that there's no phase difference between the two reflected waves. If the index of refraction is always decreasing, then there's no phase shift for either of the reflected waves, and again, there's no phase difference between the two waves. So what this means is that if the materials are in order of either increasing or decreasing indices of refraction, then the two reflected waves will experience no net phase change due to the reflections. However, if you have a material with, say, a high index of refraction sandwiched between two materials with a lower index of refraction, or you have a material with a low index of refraction sandwiched between two materials with a higher index of refraction, then you will experience a half of a wavelength phase difference between the two reflected waves. Okay, so just remember that if the materials are in increasing or decreasing order, you don't have to worry about the phase shift due to the reflections off of the two surfaces. However, if they're not in increasing or decreasing order, then those two reflected waves will be a half of a wavelength phase shifted from each other. So we have an example here which says a non-reflective coating is made out of a thin film with an index of refraction of 4/3. The film covers the lens of a camera which has an index of refraction of 3/2. The coating prevents reflections for light with a wavelength of 565 nanometers. The question asks us to determine the minimum thickness of the coating. So the idea is that because we are preventing reflections, that means that the light that reflects off of the front and back surface of this film will interfere destructively. So that way none of the light will actually reflect off of the surface of this film. So we're going to need a whole lot of room to work through this problem, so let me go ahead and open up a blank screen. So again, the basic idea behind this problem is that some of the light is going to come in and it will reflect off of the front surface of this film, and some of the light is going to travel through that and reflect off of the back surface of the film. And because this is an anti-reflective coating, these two reflected waves need to be a half of a wavelength out of phase so that they destructively interfere with each other, so we don't have any light that's reflected off of the surface of this. Now the first thing you want to do whenever you have a thin film interference problem like this is you first want to figure out whether or not there's going to be any phase differences between the reflected waves caused by the phase shifts in the reflections. So if we look at these three indices of refraction, so our indice of refraction is initially in air, so it's 1, and it's going to travel into a film, which has an index of refraction of 4/3, so that's 1.3, and then finally, the lens has an index of refraction of 1.5. So if we look at these three indices of refraction, 1, 1.3, and 1.5, we can see that they are in order of increasing indices of refraction. So what that means is that we're going to have a half of a wavelength phase shift from the light that's reflected off of the front surface, and we're going to have a half of a wavelength phase shift from the light that reflects off of the back surface of the film. So the phase difference between the two reflected beams caused by these reflections is going to be 0, because we're going to have two phase shifts that are equal to each other, so they'll cancel out. However, there's still going to be a phase shift between the two reflected beams because the light that travels through and reflects off of the back surface of this film is going to travel a little bit further than the light that reflects off of the front surface of the film. And the extra distance that this light travels is going to be equal to the length of this round trip that it travels through the film. Now, I've drawn this a little bit kind of wrong here. I have the light kind of coming in through an angle. In reality, what we have is the light's going to come in, and it's just going to hit perpendicular to the film. So some of the light's going to travel through and then reflect off of the back surface. But the reason I drew it at an angle is because here it's all going to be kind of on top of each other. So if we look at this, the extra distance that this light travels through this thin film is going to be equal to twice the thickness of the film, because the light's going to have to travel through the film once, then reflect off of the back surface, and then travel back through the film again, because it's got to make that round trip through the film. So the total distance the light's going to travel is equal to 2 times the length of the film. And if this is going to interfere destructively, this needs to be equal to 1/2 of a wavelength. And at this point, we have to be very, very careful about what we mean by a half of a wavelength, because we actually have two wavelengths in this problem. There is the wavelength of the light as it's traveling through air, and the wavelength of the light as it travels through the film. So because this extra phase is going to build up as this light travels through the film, this half of a wavelength is the wavelength of the light as it's traveling through the film, because this is where that extra phase, this 2L phase, is coming from. So this 2L needs to be equal to half of the wavelength inside the film. And remember, the wavelength inside the film is given by this formula here. So it's equal to the wavelength in air divided by the index of refraction inside the film. So now if I solve for the thickness of the film, this L, that's going to be equal to the wavelength of light in air divided by 4 times the index of refraction of the film. And if I plug these numbers into a calculator, I can see that this is equal to 106 nanometers. So that's how thick this anti-reflection coating needs to be so that the light that's reflected off of the front and back surfaces of the film will interfere destructively. And so at this point, I'm going to end our discussion on interference, and in the next video, we're going to be talking about geometric optics. So we'll talk about what happens when light reflects off of mirrors, and what happens when light hits something like water and it diffracts as it moves through that.